You know those processes in your life or your work that are basically just leaky faucets?
Oh, yeah. We all have them.
Right. You know the ones. It's like a report that always takes 3 times longer to compile than it should, or some communication breakdown that happens like every single week.
Yeah, and instead of actually getting a wrench and, fixing the plumbing, we just keep sliding a bigger bucket
Like
underneath the
this,
drain.
that's exactly a bigger and bigger bucket. And today's deep dive is all about putting down that bucket.
All right, finally.
We've got a stack of notes today, plus an excerpt from a textbook. Specifically, it's Chapter 2, Introduction to Statistical Quality Control.
Yeah, it's a great chapter.
And our mission for this deep dive is to extract this foolproof 5-phase framework that top organizations use. So you listening can stop putting Band-Aids on problems and actually cure them at the root.
Yeah, and the framework detailed in the text is known as DMAIC.
Right, DMAIC.
That's spelled DMAIC, pronounced DMAIC.
DMAIC.
Aha. Exactly. And it's basically the engine behind those massive Six Sigma quality initiatives you always hear about.
Oh yeah, Six Sigma.
Right. And its roots trace back to quality pioneers, like Joseph Duran. He realized that breakthrough improvement doesn't just happen by accident.
Yeah.
It happens project by project by following this really rigorous logic. But, and I think this is the most important thing for you listening to understand, this isn't just for factory floors.
Right. Because I read that initially and thought, well, I don't run a giant manufacturing plant making car parts,
Sure, most people don't.
But the text is super clear that this applies to literally anything, like hospital queues, bank loan approvals.
Your team's weekly meetings.
Yes.
Even your own health budget.
Exactly. I mean, if a process exists, it can be mathematically improved.
Okay, but before we get into the actual mechanics of how to fix things,
Wow.
we need to talk about the math of why we need a system like this in the first place.
Yeah, the math is fascinating.
Because the text breaks down the arithmetic of improvement, and it's pretty sobering. It really is.
Well, let's get into that. The textbook throws around terms like 4 Sigma and 6 Sigma. Before we look at the timeline, what does Sigma actually mean here?
So sigma is simply the statistical term for standard deviation.
Okay.
It basically measures variation. So in a business sense, it's a measure of how often your process fails to do what it's actually supposed to do.
Like how many mistakes you make.
Right. So if a company is operating at a 4 sigma level, it means they're producing about 6,210 defects per 1 million opportunities.
Wait, honestly, 6,000 mistakes out of 1,000,000 tries.
Yeah.
That sounds pretty good to me.
Uh.
I mean, if I only made 6,000 mistakes in my next 1,000,000 emails, I would definitely take that.
Well, sure, it sounds good until you apply it to high-stakes environments, right?
Oh, true.
Like if airlines operated at 4 sigma, planes would be landing on the wrong runways every single day.
Oh, wow. Yeah, that's bad.
Really bad. So top organizations aim for 6 sigma performance.
Which is what exactly?
A 6 sigma level is near perfection. It's only 3.4 defects per million opportunities.
Wait, going from over 6,000 errors down to 3?
Basically 3, yeah.
That's a massive leap. So how long does that actually take to achieve?
Well, this is where the textbook's math hits really hard.
Okay.
Let's say leadership rolls out an initiative, and they say, we'll aim for a 25% improvement in our quality level every year.
Sounds solid. Aggressive, but steady.
Right. But if you do the math solving for the number of years it takes to get from 6,210 down to 3.4 at a 25% annual rate, it will take 34 years.
Wait, 34 years?
34 years.
That's an entire career. I mean, by the time you actually fix the process, the product is completely obsolete and everyone who started the project has retired.
Exactly. Which is why steady incremental improvement just isn't enough for major issues.
Wow. Okay.
To reach that 6 sigma goal in a realistic time frame, let's say 5 years, you actually need a 75% annual improvement rate.
That's huge.
Yeah, and you can't achieve that by just, asking people to work a little harder. You need massive targeted breakthroughs.
So organizations must select projects that have massive financial or operational impact.
Right.
Okay. Let's unpack this, though. Let's play devil's advocate.
Sure.
If the math demands we target these massive breakthrough projects, how do we avoid picking something so huge and abstract that we just, boil the ocean and never finish?
Like what?
Like, hey, team, let's fix company culture.
Yeah. You've just identified the #1 reason improvement projects fail.
Really?
Yeah, they are way too vague. That's why the very first action required in the DMAIC framework isn't brainstorming solutions.
Right.
It's the define step. You have to define the project boundaries with extreme prejudice.
Right.
The text calls this creating a project charter. And it's not some 100-page manifesto.
Thank goodness.
It's a very tight 2-page document. It forces you to outline the specific scope, the financial benefits, and the CTQs.
The CTQs, what are those?
Critical to quality characteristics. Basically what actually matters from the customer's perspective.
Oh, got it. So if it takes you more than a few days to write the charter, your scope is probably way too big.
Exactly. Or it means you don't actually know what the problem is yet.
Right. You're just looking at symptoms.
Yes. And to prevent that, the text introduces a really great visual tool during this initial phase called a SIPOC diagram. SIPOC.
Okay, the textbook gives a really relatable example of this using internal office coffee.
Oh, the coffee example is perfect.
Right. Let's say a company wants to improve its coffee service because employees are always complaining it's slow and tastes awful.
Right.
Before using SIPOC, management might just, buy a new coffee machine and call it a day.
And the coffee might still be terrible.
Exactly.
Because the machine wasn't the root cause. SIPOC stops you from jumping to conclusions by mapping out the entire chain.
SIPOC. So what does it stand for?
It stands for suppliers, input, process, output, and customer.
Okay, let's walk through that with the coffee example.
Sure. So the suppliers are the utility company providing the water, the vendor providing the beans, the company providing the filters.
Right.
The inputs are the specific ground coffee, the actual water temperature, the electricity.
Makes sense.
Then the process is the human action, collecting materials, brewing, pouring.
Okay.
The output is the hot brewed coffee, and the customer is the employee drinking it.
Wow. Breaking it down like that really makes you realize that a bad cup of coffee isn't just bad coffee.
No, it's not.
It's a failure at a highly specific point in a chronological chain. I mean, maybe the supplier changed the bean roast or the input water temperature is just too low.
Exactly. And once you visually map a process, especially in service or transactional businesses where you don't physically see a widget moving down a conveyor belt, the invisible suddenly becomes visible.
You can actually see the borders of your problem.
Precisely.
Okay, so we've got our charter and we've drawn our SIPOC map. I know what the boundaries are. But my instinct now, as a manager, would be to look at that map, guess that the intern is putting in too much water, and just mandate a new rule tomorrow.
And that is the second trap.
Oh.
Moving from mapping right to guessing.
Right.
The framework demands we move from assumption to hard statistical data. We enter the measure phase.
Okay, so how do we do that?
We have to establish a true baseline of how the process is performing right now, today, before anyone touches it.
But how do we actually measure it without getting buried in completely useless data?
The text introduces two crucial concepts here, KPIVs and KPOVs.
Okay.
Key process input variables and key process output variables. Let's ground this back in your coffee example.
Okay, so a KPIV, the input variable, would be the exact ratio of coffee grounds to water.
Yes, that is something you can directly control and measure.
Right.
The KPOV, the output variable, is the result. In this case, maybe it's the bitterness score given by the employee drinking it.
Or the time it takes to brew a pot.
Exactly. You measure both to find the mathematical relationship between the inputs you control and the outputs the customer actually cares about.
So you aren't just observing, you're quantifying the current state.
Yes.
And once you have that baseline data, you enter the analyze step.
Right.
The text makes a really sharp distinction here about dividing the root causes of our problems into two distinct categories.
This is so important.
Common causes and assignable causes.
Yeah, this distinction changes how you view every problem in your life.
Really?
Oh, absolutely. A common cause is a source of variability that is embedded in the system itself. It's just the background noise of the way things are currently built.
Okay.
An assignable cause, on the other hand, arises from a specific external abnormal event.
Let me try an analogy to make sure I'm grasping this.
Go for it.
Think about your morning commute. A common cause of you being late is just standard rush hour traffic.
Right.
The system itself, the highway at 8 a.m., is inherently congested.
Yes, and you can't fix that traffic by driving a different car. You have to fundamentally change the process, like leaving an hour earlier or maybe taking a train.
Exactly. But an assignable cause is if a mattress falls off a delivery truck and blocks 3 lanes.
Yes.
That's a specific external freak event. You don't redesign your entire life schedule and start waking up at 4 a.m. every day just because a mattress fell off a truck once.
No, you just need to remove the mattress.
That's a vital realization. I mean, if you treat a common cause like an assignable cause, or vice versa, you're going to waste a fortune over engineering a fix for a freak accident.
Or you'll completely fail to fix a broken system by just blaming individual events.
Okay, but even if we successfully separate the causes, our baseline data might reveal like 50 different things wrong with our process.
Very true.
How do we prioritize them so we don't just paralyze ourselves with analysis?
The text highlights an incredible tool for exactly this scenario called FMEA.
FMEA.
Yeah, failure modes and effects analysis. It takes the emotion and the loud opinions completely out of what to fix. It forces the team to score every potential failure on a 1 to 10 scale across 3 very specific categories.
Let's break those 3 down for the listener.
First is likelihood. Basically, how often is this specific failure going to happen?
So a 10 is bad.
Right. A 10 means it happens constantly. A 1 means it's incredibly rare.
Okay, what's next?
Second is ability to detect. If it goes wrong, how likely are we to notice it before it hits the customer?
Oh, interesting.
Yeah. So a 10 means it's completely invisible to us until the customer actually complains. A 1 means our internal alarms go off immediately.
Got it. And the third?
Third is severity. If it happens, how bad is the impact?
So a 10 on severity is a catastrophic financial loss or like a safety issue.
Right.
While a 1 is just a minor typo on an internal memo.
Exactly. And once you score a failure, you multiply those 3 numbers together. Likelihood times detection times severity.
Okay.
That product gives you your risk priority number, or RPN.
Let me do the math. So if a failure happens all the time, let's call it an 8.
Okay.
We can't detect it, so that's a 9.
Right.
And it's highly severe. A 10, that's 8 times 9 times 10. So an RPN of 720 out of a possible 1,000.
Bingo. And suddenly, prioritizing is easy. You simply rank all your failures by their RPN and tackle the highest numbers first.
Oh, wow.
You no longer argue in a meeting about what's most important. The math just tells you.
It's pure logic.
Yeah.
And the text also mentions a really fascinating way service businesses analyze these high-risk areas without disrupting their actual business.
Oh, the computer simulation.
Yes.
Yeah.
Something called discrete event computer simulation.
This is crucial for environments where human beings are the variables.
Right.
If a bank is trying to fix a massive backlog in loan approvals, they can't just start experimenting on real customers. That's too risky.
So they build a computer model.
Exactly.
Right.
They simulate the arrival rates of loan applications as random variables. They can test how incomplete forms or credit check delays cause bottlenecks. And they watch the digital backlog grow or shrink safely inside a computer before they ever touch the real-world process.
Okay, so let's say we've done the math. We have our baseline data, we've used FNA to find our highest risk priority number, and we know exactly what's broken.
Sounds good.
I'm ready to roll out the solution to the entire company on Monday morning.
Please don't do that.
Wait, why not? We did the math.
Because that brings us to the improve phase. And the key rule here is that finding a solution doesn't mean yelling Eureka and initiating a massive overnight overhaul.
I mean, but we know it's going to work.
You think you know. But introducing a new variable into a complex system almost always breaks something else you didn't anticipate.
Oh.
You must use pilot testing.
Right.
Teams use what are called designed experiments to test solutions in controlled environments. The text highlights a fascinating example of a bank trying to improve service quality at its branches.
Yes. The bank identified their CTQs, their critical to quality metrics, as speed, consistency, and a pleasant physical environment.
Exactly. And they brainstormed 2 potential improvements. First, installing brand new physical workstations for the tellers to speed up transactions.
Okay.
And second, implementing a new, intense training program for the staff.
But instead of just guessing which one would work better.
Or rolling both out to all 500 branches at once.
Right. They ran a 30-day block experiment across just 4 physical branches.
Yep. It's brilliant.
I loved this part.
Right.
Branch A got the new physical workstations but no training.
Okay.
Branch B got the training but kept the old desks.
Right.
Branch C got both the new workstations and the training. And Branch D got neither. They were the control group.
It was a physical, real-world experiment, and the data proved that the workstations alone or the training alone barely moved the needle.
Wait, really?
Yeah.
Neither worked alone.
Barely. It was the interaction of the two, a combination of both the new workstations and the new training, that yielded a statistically significant improvement in customer satisfaction.
Wow.
By piloting it, they saved millions by not rolling out a half measure that just wouldn't have worked.
Okay, so Branch C is booming. The customers are happy. The math worked. The project is officially a success. We can pack up and move to the next leaky faucet.
And that assumption right there is exactly where 90% of improvement projects die a slow death.
Really? Why?
Because human nature dictates that within a month or two, those tellers are going to find workarounds, they'll skip the training protocols, and revert right back to their old broken ways of doing things.
Wow, so gravity just pulls the system back to chaos.
Always. Which is why the final requirement of the DMAIC framework is to institute a strict control plan. You have to institutionalize the gain.
The control feeds.
Yes. You cannot rely on willpower or a motivational speech. You hand the newly improved process back to the daily operators along with updated training documentation, automated alerts, and statistical control charts.
Control charts.
Yeah, visual charts that will physically flag if the process starts drifting back toward the old baseline.
You essentially build a fence around the new process.
Exactly.
But I have to ask about a glaring vulnerability here.
Sure, what is it?
We've talked about defining the scope, measuring the baseline, analyzing the root cause, pilot testing the improvement, and building a control plan.
Right.
This sounds like it takes months.
Yeah.
What stops a team from completely defining the wrong problem in week 1 and not realizing it until they're pilot testing in month 4?
That is exactly why this framework includes mandatory safety nets called toll gates.
Toll gates. Okay.
These aren't just casual check-ins. Toll gates are strict, formal review meetings held between every single major phase we just discussed.
It's sober. Before you were even allowed to start collecting baseline data, you hit a toll gate.
Yes. At a toll gate, the project team must present their work to management and the ultimate owners of the process.
Got it.
For example, at the very first toll gate, management will scrutinize the project charter. They will ask, does this problem statement focus purely on the symptoms, or did you accidentally write down your preconceived solution disguised as a problem?
So you can't sneak your pet project through.
Nope.
You can't just say, the problem is we don't have the new software I want. The toll gate forces you to prove you've done the unbiased work before you're granted the resources to pass through the gate to the next phase.
Exactly. It stops you from wasting time on a completely flawed premise.
That's incredibly smart.
It is. Now, all of these mechanics, the toll gates, the FMEA math, the pilot testing, they can sound highly theoretical until you see them released into the wild.
Yeah, let's look at some real-world examples.
To truly understand the power of this framework, we need to look at what happens when millions of dollars in critical business relationships are on the line.
The textbook details 2 massive high-stakes case studies that prove this isn't just for factory floors. Let's start with the legal world. The DuPont litigation case.
Oh, this is a masterclass in fixing a transactional process.
Right.
A corporate legal department at DuPont was drowning in documents for a specific massive piece of litigation. We're talking millions of pages of evidence.
Millions.
And the process of managing, indexing, and retrieving these documents was almost entirely manual.
Which means it's incredibly vulnerable to human error.
Absolutely.
I mean, if a lawyer needs a specific contract from 3 years ago by 5 p.m., someone has to physically go find it in a cardboard box.
And they frequently couldn't find it. They were suffering from lost files, incorrectly copied documents, and they were incurring incredibly costly court extensions because they just couldn't meet the 30-day deadlines.
Wow.
So a project team stepped in. In the initial define phase, they set clear boundaries. Reduce cycle time, reduce errors, and cut costs. No boiling the ocean.
Then they mapped out the manual nightmare and gathered the data. And the analyze phase revealed root causes that weren't just, we have too much paper.
Exactly. The FMEA tool and their analysis revealed underlying organizational issues, like an incredibly high turnover rate for the clerks handling the paper.
Right. Why were they leaving?
Because the job was tedious, the training was completely inadequate, and there was zero process ownership. The clerks didn't feel invested in getting it right because the system basically set them up to fail.
So they hit the improve phase, right? The pilot testing.
Right.
And their solution was digital scanning. Now, the really interesting thing here is DuPont had actually considered digital scanning before this project.
They had.
But management had always thrown the idea out because they just assumed the upfront technology costs were far too expensive.
Right. But because the team had rigorously measured the baseline during the measure step, they now knew the true cost of the broken manual system.
Oh, right. The hiring cost.
The constant hiring and training of new clerks, the lost hours searching for files, the actual court penalty fees.
It adds up fast.
Armed with that hard data, they proved mathematically that scanning wouldn't be an extra expense. It would actually reduce the cost per page by 50%.
That's wild.
Yeah.
Think about how that applies to your own listening. your digital clutter or life admin.
Yeah.
You might think setting up automated rules for your inbox or a strict filing system takes way too much time up front. But if you actually measure the hours you waste searching for lost emails or missing tax documents over an entire year, the return on investment becomes completely undeniable.
Absolutely. For DuPont, the result was a pilot program that saved $1.13 million initially.
Wow.
And once they passed through the final toll gate and scaled the control plan across the company, the savings hit about $10 million.
$10 million, just by replacing a leaky bucket with a solid pipe.
Exactly.
Now, the second case study in the text is equally compelling, but it deals with the supply chain.
Yes, the machine tool manufacturer.
Right. They were facing massive financial penalties. Their on-time delivery to a key customer was stuck at a dismal 85%.
And this wasn't just some small customer. They represented $8 million in immediate business.
Oh, wow.
Plus, the contract had a brutal penalty clause. The manufacturer lost 15% of the price of each tool for late delivery.
15%.
Yeah. They were bleeding about $60,000 per late shipment and were literally on the verge of losing the client entirely.
Okay, so the goal was defined simply: achieve 100% on-time delivery.
Right.
The contractual lead time was 8 weeks from the moment the purchase order was signed to the moment the equipment actually shipped. By looking at historical data, they mapped the process to find out why that 8-week window was impossible to hit.
And what did they find? It wasn't just one massive bottleneck.
No.
It was a combination of culprits across completely different departments.
So what were they?
First, supplier quality issues.
Yeah.
Parts from outside vendors were failing during final assembly testing, causing massive delays.
Okay, that's one.
Second, internal administrative delays. Purchase orders were sitting in a single person's inbox for days before the engineering teams even knew they existed.
Oh, that is so frustrating.
Right. And third, it was taking up to 3 days just to get the customer to confirm the final equipment configuration.
Because the customer's own ordering process was confusing, leading to miscommunications and rework mid-manufacturing.
Yes.
I mean, think about how often that happens in our own communication loops, waiting days for an email reply just to clarify what someone actually wants.
It happens all the time. So in the improve and control phases, they didn't just yell at people to work faster.
Right.
They redesigned the actual architecture of the work. To fix the supplier issue, they didn't just ask for better quality, they implemented a strict internal buy-off checklist the supplier legally had to complete and submit before shipping any parts.
Nice.
To fix the internal delays, they eliminated the single point of failure by creating a shared email inbox accessed by 3 different people.
A simple, almost boring administrative fix, but highly effective.
Very. And to fix the customer confusion, they literally sat down with the client and designed a customized spreadsheet for orders that lived in a predefined shared web location.
Oh, I like that.
It forced the customer to take ownership of the exact configuration up front before the 8-week clock even started ticking.
And the result of standardizing those touch points, they hit 100% on-time delivery.
Yep.
They saved over $300,000 in penalties every single quarter, and they salvaged an $8 million relationship.
All because they used data to find the root causes, tested their improvements, and put a control plan in place like that shared spreadsheet with firm milestone dates. So the process just couldn't revert back to chaos.
Okay, so to summarize this entire framework for you listening, stop guessing what's wrong with your workflows.
Please stop guessing.
Define the exact scope and financial impact so you don't boil the ocean. Measure the specific inputs and outputs to get a real mathematical baseline. Analyze the root causes, using logic tools like FMEA to separate the embedded system failures from the freak accidents. Pilot test your solution before you overhaul your whole life.
Crucial step.
And finally, put a control plan in place so the process never breaks again. Oh, and use those toll gates, strict reviews with yourself or your team to keep from going down the wrong path.
That's a perfect summary. And if we connect all of this to the bigger picture, I want to leave you with a final thought regarding that final step control.
Okay, what is it?
The textbook explicitly notes that transition plans require a validation check several months after the project is actually completed.
Why so late?
Because things so frequently go wrong once the excitement of the initial fix fades. Think about the habits or the systems you've tried to improve in your own life.
Oh, yeah.
What if the true test of a solution isn't whether it works flawlessly on day 1, but whether the system naturally rejects the fix by day 100?
Oh, wow. That reframes the whole concept of self-improvement.
Doesn't it? How can you design improvements in your own life that actually want to stay fixed?
Right.
How do you build an environment where doing the right thing is the path of least resistance, rather than relying on sheer exhausting willpower to maintain it? Because, willpower fades, but a well-designed system endures.
So the next time you find yourself reaching for a bigger bucket to slide under that leaky faucet, stop. Grab a piece of paper, write down your project boundaries, and go fix the plumbing for good.